Hello, good morning, good afternoon. I think I'm ready now. Okay, do you see the desktop and hear me? Is everything seem okay now?
Yeah.
Okay, okay. All right. So first thing today, there's a new homework assignment up there, but we're not going to talk about it yet. I'll just show you. It's it's up there. It's been up there since last night. Okay, and like usual, it's got the explanation. It's not as long. It's nowhere near as long as the last program assignment. So it's got an explanation and a zip file. It's about paging virtual memory, which we'll start talking about on Wednesday. So you can read the assignment, but we have uh, in the course website, there's a reading assignment for the next chapter of the book, which is starting on paging. So you can read that and you can look at the homework assignment, and we'll talk about it in more detail on Wednesday. But the bottom line is that you have to write a little bit of code. You write one line of code in each one of these case statements. One or two lines of code for each case statement. We'll talk about what you do, but it's not writing a lot of code, but you have to read a bunch of documentation because each one of these case statements is solved by a function in the Windows operating system. So you have to learn how programs talk to the operating system about virtual memory. That's what this program assignment is about. We're learning the code that a program uses to talk to the operating system about virtual memory. And in the homework assignment, at the bottom, these are the functions. Uh, Virtual alloc for allocating virtual memory. This is the basis of how malloc is actually written. What you're learning is like what is there underneath programs like malloc that allocate memory. Hey, but malloc is a C level well, malloc is a C level memory allocator. This is operating system level. So these are the tools that malloc itself would be using. If you were if somebody gave you the job of writing the malloc function, you would need these functions to do it in. Okay, so this is the documentation. So you have to read. There's a 1, 2, 3, 4, 5 functions, and in the zip file with the class with the zip file for the homework, I gave you a chapter of an old Windows programming book on the virtual memory functions. Okay, so I scanned in these pages. It's 8 pages. So it's hard. It's the only book I could find that had a nice explanation of these functions. So so this reference here. Okay, these 8 pages of the virtual functions, the uh, virtual alloc, virtual free, virtual lock, virtual unlock, and this is all of them. I mean, I gave you a link to all of the virtual memory functions, but you don't need the rest of them. The ones you need are these: virtual alloc, virtual free, virtual lock, virtual unlock. Okay, all right. So that's the homework assignment. You're going to learn how to write Windows memory management programs. How does a how does a C program talk to the operating system about memory? Okay, so we'll say a lot more about that on Wednesday. Okay, and
Professor, I have a
yeah,
question.
mhm.
Are we gonna know our grades for the previous homeworks and midterm before the drop date?
I'm trying to. Um, yeah, I'm trying. They they gave me 160 students this semester. I I'm trying very hard to get some of the grades done. If any individual is worried about their grade, send me an email and I'll try to look at those in particular. But the truth is, I'm having a very hard time keeping up with this many students. Yeah, yeah, it's huge amount of work. So if you're if you want to know, I can see some people may not be worried, but if someone is worried, then I could look at their grades, immediately. Okay, but I've been working on the grading, but it's so much that yeah yeah but like I say, if you have it if you're specific if you're worried about your grade, please send me an email. Okay,
Thank
so,
you.
okay, um, let's see. All right, so what we need to do today, okay, we'll look at the homework assignment on Wednesday. We're gonna talk about the next stage of virtual memory after uh, base and bounds is something called segmentation. Okay, and segmentation is actually just a generalization of base and bounds. So it's pretty easy to talk about segmentation. The next step, paging, is a fair amount harder. So we're working our way up to paging, which is the real way that modern operating systems do virtual memory. Though segmentation is built into the Pentium, the thing we're talking about today, segmentation, is not that old. I mean, the Pentium computer has it built in. I think maybe the Linux operating system even makes some use of it. Windows, as far as I know, makes no use of it. It's something built into the Pentium computer that, as far as I know, Windows turns it off. Okay, so it was really something more from the 80s and 90s. But so it's not that old of an idea, and it helps it studying it helps to build up to studying the paging system. Okay, so now let me. Oh, I need a picture. Um, I took the picture we've been using of a memory management unit, and I exaggerated the size of the memory management unit. I want a big memory management unit. So we're going to talk today about an idea that's going to need a much bigger memory management unit. So here is what we did the other day. Okay, so what we talked about was base and bounds. Each process has a base and a bound register. And this register is just like these registers. Think of it as the CPU has grown. So these registers belong to a process just like these do. So when a process is swapped out, when a process is not running, when it's in a block state, these registers would be in the process control block along with these registers. So when you do a context switch from this process to that process, so from process 0 to process 2, you would take all his registers, you take all of process 0's registers, including the memory management unit, the base and bound register, put them in the process control block. Then you'd go to his process control block and copy everything in. So the process control block now includes the base and bounds registers. Okay. The base and bounds register create this virtual memory space that we've just drawn over here on the left. In this process, as far as the CPU is concerned, that's address 0, because that's what happens is that the CPU will spit out address 0. So address 0 goes in here, gets added to the base register. The base register, then base register plus 0 would be there. So that's address 0 from the point of view of the CPU. So when the CPU is in user mode, the CPU sees that and thinks it's all of virtual memory. So what the CPU sees is that and thinks that's virtual memory, that's address 0 and that's the maximum memory location. Then when you're switched to this process over here, then the CPU is all of a sudden seeing, well, it thinks it's seeing the same virtual memory space, 0 to whatever, but now it sees it from here to here. This is the new 0, and this is the new upper limit. Notice that the upper limit here won't be as big as this. In this system, the CPU never quite knows how big virtual memory space is. So we haven't really quite created this virtual memory system. I said here that this is size 0 to 2 to the n minus 1, which is where n is the width of that word. Okay, in this memory system, every virtual memory space is a different size, depending on what the bound register is. So it's a bit of a quirky virtual memory system in that the virtual memory space that the CPU thinks it's looking at, it might think it's this big, but the bound might cut it off. So if the CPU tried to talk past the bound, remember that'll be where this error interrupt comes in. If the address that comes in here is larger than the bound, if it tries to go beyond this bound here, then the process, the memory management unit interrupts the CPU and halts the process. Okay, so each virtual memory space has got its own size set by the bound register of the memory management unit. But the more important thing is that every virtual memory system thinks it's got its own zero. So to the CPU, memory seems to start there and go to some upper limit. Then when the CPU is running this other process, memory seems to start there. There's no way for the CPU to talk to that memory location in user mode. That would require a negative address to come out of here, but these addresses are always treated as positive numbers. They're always added to the base. So there is no negative addition here. There's no negative numbers. So the CPU can't see that way. And the CPU can't see that way because the bound register stops it. Okay? So it can't go backwards because there's no notion of a negative address, and it can't go beyond the bound because that's just what the bound register is there for. So the CPU thinks this is all of memory. Okay. Then when it switches to this other process, it thinks that's all of memory. Then when it switches to this other process, it thinks that's all of memory. Okay. And when the CPU is in kernel mode, it sees all of physical memory. And there's different ways of thinking of that. One way of doing that would be in kernel mode, the base register is 0 and the bounds register is the largest physical address. That would be the simplest way to do it. That in kernel mode, the memory management unit is turned on, but when you trap into kernel mode as part of the process of switching from user mode to kernel mode, the base register would be set to 0, physical address 0, and the bound register would be set to the highest possible memory address. At that point, every PC address becomes a physical address. It's still a virtual address, but it's also a physical address because the memory management unit is set to 0 and 2 to the m minus 1. M is the number of bits in the physical addresses. N is the number of bits in the virtual addresses. That's the width of these words here. Okay. All right. So that's base and bounds. Now this works pretty well. Okay. Its advantages are, let's see, can write them down. I can't remember. I think we wrote them down, but we should do it again. Okay. If you use base and bounds, one issue that we can do is, one advantage is something called solving external fragmentation by relocation. Okay. External fragmentation is these chunks of memory you see loose over here. See, if you look at this picture, there's a free chunk of memory there, unused chunk of memory there, unused chunk of memory there. If a new process comes in, it needs a certain amount of memory that's a little bit more than this, but less than this one and this one combined. Right now, you couldn't run that process because there's not enough room there and there's not enough room there. But if you slide that process up, that's called relocation. You could coalesce that free chunk of memory with that free chunk of memory and then run a process in the coalesced chunk. And when you slide him up, all you have to do is change his base register to the new base and change his bound register to the new bound, and then do the copying. Okay, this is referred to as relocation. The fragmented memory that's outside of the process is called external fragmentation. Okay, then in a minute we're going to talk about something called internal fragmentation. Fragmentation is when there's wasted memory. So fragmentation means memory's cut up in chunks, and the chunks are separated from each other, and you can't use these unused chunks because they're not quite big enough. So that's a fragment. Fragmentation refers to these fragments of unused memory. Okay, so people use these words for hard drives too, for storage space on hard drives. A fragment is an unused chunk of memory. Okay, fragmentation is that memory is being cut up into lots of little unusable chunks. And you want to solve the external fragmentation problem, in this case by relocating, sliding processes up or sliding them down so that these free regions get coalesced. Okay, base and bounds does this okay. It's time consuming to slide a process up in memory. The CPU has to halt all the work it's doing and just start copying bytes up this way. You'd have to start copying bytes up this way. Maybe this processor would copy bytes down. Okay, and so that's done by the kernel in kernel mode. It has to access all of memory, and while it's doing that, no useful work is being done. Okay, but base and bounds, that's one of its big advantages. It solves external fragmentation. Okay, and another thing that it solves is processes can grow. A process can ask the operating system, the process can say, oh, I want to read a large data file. I need more memory. So the process can ask for a larger bounds. Okay, so the process can say, I want my bounds register increased. Now, in this case, if there's a fragment there, the process could grow into that fragment. Also, the operating system could just relocate this process by sliding it down and then even have a bigger chance of growing the bounds register. So a process can say to the operating system, can I please have more memory, virtual memory, okay, by increasing its bounds register. And yeah, the operating system can reply with an error saying, no, there's no more free memory, or the operating system can request like if a program asks for a megabyte of more memory, the operating system might give it a half a megabyte if that's all that's available. But at least a process can request more memory. A process can grow. And a process can, even if it wants to, shrink itself. If a process has asked for more memory, used it up, and no longer needs it, it could tell the operating system to shrink it, to shrink its bounds register so that now there's memory for somebody else to use. Okay, so processes can grow and shrink if they want. Okay, growing is actually probably more important than shrinking from the point of view of most processes, but either way it'll work. Processes can grow and shrink. Okay, now I mean, of course, the zeroth thing that this thing gives us is that's the real thing that this thing does for us. It gives us memory protection. That's what it's really designed to do, to provide this process, protect it from other processes. No other process can reach inside of that memory space, and it protects the operating system from all the processes. So it protects processes from each other. It protects the operating systems from the processes. So the absolute most important thing that base and bounds is giving us is memory protection and the notion of virtual memory. Oh, actually, memory protection. Actually, let me say that this would be the first one, and then the second is just the there's a that's actually real quick. We mentioned it briefly. What do we mean by the notion of virtual memory? That means that the compiler can compile for virtual memory. Okay, the compiler, when it compiles code, can say, when it's creating the exe file, it could say that all the variables are based off of 0. It can just assume this idea of virtual memory. So this makes life for compilers way easier. The compiler just assumes that a program runs starting at memory address 0. That's its base. And then all the code and data is just going to be put in memory past memory location 0, as if there was only one program running in memory. So when the compiler compiles your program, it can pretend that your program has all of memory and it's the only program in memory. Okay, so that's a huge advantage from the point of view of the compiler and other programs too. What we might call just the notion of virtual memory, that every program thinks it owns all of memory, but actually it owns all of virtual memory, but it thinks that for all the compiler knows when it's compiling your program, this is all of physical memory. Okay, so the most core benefit is memory protection. Then the next benefit is just this notion of virtual memory, that the compiler doesn't need to know that your program is going to be located at that physical address. And there was a time in the old days when programs had to be written for specific memory addresses. So memory was divided up where one program would run a certain range of addresses, another program would run at a certain range of addresses, and each program had to be written for its range of addresses. That would be going back all the way to the 50s and so. But you know, that was not very good. Programs couldn't, you couldn't run a program on another computer. You couldn't run a program at another memory address. Okay. All right. So the notion of virtual memory is a pretty good advantage. It makes things much easier for writing compilers and other tools. There's lots of the tools that make an operating that make uh, like getting your another tool besides the compiler is the what's called the loader, the thing that puts your program in memory. When you double click on an EXE and you want to run a program, somebody has to copy the program into memory. That's a part of the operating system called the loader. Well, the loader doesn't care where it loads your program. Wherever it just looks for a place big enough to hold it. That makes the loader real easy to write. It might need to shift things around to make room for your program, but it doesn't need to worry about what address it puts your program at. So the compiler has an easier job. The loader has an easier job because of this notion of virtual memory. Okay, and then external fragmentation is solved because it's relatively easy to move these processes. It's time consuming, but when you move a process, you just change its base register and its bound register, and then the process is good to go in a new location. And processes can grow and shrink. Okay, so that's what we have with base and bounds. Now, there's a couple things that are missing. Okay, what we also want to be able to do is there's something called internal fragmentation. We want processes to be able, another thing we want to be able to do is share memory okay. We want to be able to share memory, and another thing we want to be able to do is, this one's kind of weird. Can a process have more virtual memory than there is physical memory? Yeah. We'd like to have a system where a process, like suppose you have 8 gigabytes of physical memory, but a process wants 20 gigabytes of memory. Can you do it? Can a process think its virtual memory space is actually larger than the physical memory space? And the answer is we would like to be able to do that. We'll see how to do that, but we'll end up right now. Notice that the virtual memory space is always smaller than the physical memory space. By the very definition of base and bounds is that the base and bounds have to be addresses within the physical memory space. So one disadvantage of this system is that every virtual memory space is smaller than physical memory spaces. So that's a kind of a thing over here. It's not an advantage. It's just something to note. Over here, you can say that the virtual memory space is always smaller than physical memory. Okay. So it's an important note. Every virtual memory space is always smaller than the physical memory space with base and bounds. Okay. You can't give a process, you could give a process almost all of physical memory, but you can't give it more memory than there is physical memory. Okay, so that's something to note about base and bounds, and that's one of the things we want to fix. Okay, all right. Now, these three things here can be fixed by having what it's called segments, but the best way to think about it is just multiple base and bounds registers. Let's give a process multiple base and bounds registers. So that's this picture over here. I want to fill this in. What I'm going to do is give, let me open this in Paint. It's actually not a hard, it's not really complicated idea. So it's a fairly straightforward, oops, where's that folder? It's okay. So we'll just call, let's give the memory management unit, say, just a bunch of base and bounds. So this will be base and bounds 1, then base and bounds 2. Let's give it 3 base and bounds registers, 3 base and bounds pairs. Okay. We'll see what we can do with them. They're actually going to act exactly like the other ones do. Okay. So so call this base 0, base 1, and base 2, and then call this one, say, bound 0, bound 1, and bound 2. So 3 pairs of base and bounds. Okay, right. Now, let me put a process in memory, say. So here's some, well, let me, here's my, let's see, this picture doesn't quite fit. Here's my virtual memory space over here. Now, let me think of the virtual memory space as being cut up into parts. Remember, virtual memory would include the code, then down here, there might be the stack, and then there would be, say, the heap. Okay, so we would have code, stack, and the heap. Every program is going to have at least a code, a stack, and a heap. Okay. Now, in the textbook, that would be this picture that we saw before. It's actually the pictures. The picture shows up in the book over and over again. This. Every process has code, heap, and stack. Here it's shown as one big chunk. That's how base and bounds by itself would do it. This would be, the base address would give you your 0 location, the bounds address would give you your top location, and that would be a picture like this, where the code was up here. So in this picture here, the code would be up here, then below, that would just be this sitting inside of here. And then the same 3 regions would be in here. Code, then, here, they have code, then heap. Notice that there's a bunch of free memory here, and then the stack. This is unused memory that the heap can grow into, or the stack can grow into. And this is important. This is one of our ideas. This here is going to be called the internal fragmentation. Remember, I said fragmentation is when memory is in chunks that aren't being used. Okay. Over here, let's see. So many pictures. Oh, I'm sorry. Yeah, over here, these were chunks of unused memory that were not being used by any process. Okay. This is unused memory that belongs to a process, but the process isn't making use of it. So this unused memory is sitting inside of that process. And there's some unused memory sitting inside of this. This unused memory here is called external fragmentation. This is called internal fragmentation. Okay. Base and bounds helps with the external fragmentation because you can defragmentate by sliding processes up and sliding them down to coalesce the external fragments. But base and bounds, just when you slide this process up, the internal fragmentation just slides with it. What now with multiple base and bounds registers, we can solve the internal fragmentation problem too. That's what we're going to show in a second, is how to get rid of this internal fragmentation, or at least mitigate it, how to mitigate this internal fragmentation a little bit. Okay, so right now, what we'll do is we'll have a process. Okay, it's got its code piece, its stack piece, and its heap piece. If I drew it the way they did it, I would have drawn the stack or the heap right next to the code, and then the heap grew down and the stack grew up. But what we're going to do now is to say we're going to have a code base and bounds register, a heap base and bounds register, and a stack base and bounds register. So what it'll look like is over here, I'll put, say, code here. Whoops. So for this process, I'll put the code here, put the stack maybe right there. Doesn't have to be with the code. Yeah, what it is I'll put these where I can find room for them in the, if there's externally fragmented memory, when it comes time to load this process, I'll look for a chunk that's big enough to hold its code. So this will be, so this is process 0 code. This will be process 0, say, heap. And this will be process 0's stack. Okay. Now, maybe there's another process in memory. Here's another process. So over here, I would have, say, process 1 heap. And maybe this would be process 1 stack. And then this would be down here, process 1's code. Each process has 3 base and bounds registers. Okay. Now, if I'm running process 0, this base register would point to there. That's that'll be the code base. This register will point to there. That would be the heap base. And this register would point to there. That would be the stack base. Whoops. Okay. And then this bound would point to there. This bound would point to there. And so it's pretty straightforward. It's just base and bounds over and over again. Okay. Now, all these registers are now part of the process control block that belongs to each process. So each process has a process control block that goes with it. So there is a process control block down here for process 0. So there's the process control block 0. And then there's another process control block. There's a process control block for process 1. Okay. When the operating system says that the CPU is running process 0, the base and bounds registers belong to process 0. Then if there's a context switch from process 0 to process 1, all these registers, all the base and bounds registers, along with the CPU registers, get put in process 0's process control block. You go over here to process 1's process control block, and you load everything from here into the CPU registers in the memory management unit. And then this base register will be pointing to down here. Notice that this is the code. If we think of this as code, heap, and stack base and bound registers, then when you update this, the code will go from here down to here. Okay. Now, what does this do for us? Okay. It helps solve this internal fragmentation problem. Okay, what you're going to do now is give each process a medium-sized heap and a medium-sized stack. Okay, instead of giving it all this space, instead you might give it a stack. You might say, well, give it a heap that's about that big and give it a stack that's about that big and not have to have so much space in between them. Then if a program needs a bigger heap, instead of just growing here until it hits the stack, we said before that if you ask the operating system to increase your bound register, you can grow the heap. So the heap can grow down this way. And then if it hits that bound, it can just ask the operating system for a bigger bound. Notice that that couldn't even be done over here. If this guy hit the stack, the program crashed. In this model, which is the model that will be over here, if the heap grew and hit the stack, you're just dead. You can't do anything. Well, actually, no, here, I'm sorry, we would have to, we could grow the bound, but then the program would have to know how to move its own heap and stack around. So if you increase the bound, if the heap grew and hit the stack, they tried to do this in the old days and it didn't work. That's why they invented this multiple base and bounds. If the heap hit the stack, well, you could ask for a larger bounds, but then you'd have to push your stack down to make room for the heap, which is nearly an impossible thing to do. The stack is way too complicated to just move it. Okay, I don't, moving a stack. I mean, I think they actually did do these kind of things, but it's really slows things down. It's immensely complicated. Somebody has to write really super tricky code to analyze the stack and then relocate the stack. Okay, not good things to be spending CPU time on. So in this system here, if the stack was growing down and the heap was growing up and they met in the middle, the program could say, okay, move my bounds, give me more memory, but then it would have to move either the heap or the stack and to free up space in between. Okay, so this doesn't work very well. But in this new system, it works actually very well. If the heap is growing down and it hits this bound, well, it can just ask the operating system for more space. The operating system might need to relocate it, but then that's a straightforward relocation because it's based on a base register. It's virtual memory that's being relocated. So as we said before, relocating virtual memory, everything is based on address 0 anyway. This is an address, it may be worth putting in here that all of these that's an address 0. Whoops. Every one of these is an address 0. That's an address 0. That's address 0. Each one of these is an address 0, so they're easy to locate because all the code in them is based on 0. So here's another address 0. This is another virtual address 0. All of these think they have virtual address 0 at the top of these segments. Okay, now these are called segments now. Each one of these chunks of virtual memory is called a segment. So a segment is the region between a base and a bound register. So segment 0, segment 1, and segment 2. And here I'm using the segments for code, stack, and heap. Okay, so if a heap needs to grow, there might be space that it can just grow into. The operating system might be able to just change the bound register and then everything's good to go. The heap can keep growing. The heap would be growing in the direction of increasing virtual addresses. Nothing from the point of view of the heap, even if it does get relocated, it doesn't know it. If the heap does get relocated to somewhere else, the heap doesn't know because it still sees everything is based on at 0. The heap thinks that, the heap now thinks of these as 3 address spaces. So in a way, the program, when people wrote programs like this, they didn't think of it as like this picture here. They actually thought of a program as 3 segments. So this is really not the right picture over here. The program would really be thought of as a code segment that has its own address 0, a stack segment with its own address 0, and a heap segment with its own address 0. So this would actually over here be thought of as a this is really 3 virtual memory spaces over here. So even over here in virtual memory, this is still an address 0. This is still an address This is still an address 0 here, and this is actually still an address 0 over here. The program is really going to be three virtual memory spaces. Yeah, that's one quirk of this. The way to think about it in this system is that a process is multiple virtual memory spaces. Okay, so instead of being one virtual memory space cut up, it's actually going to be thought of as one virtual memory space, another virtual memory space, and another virtual memory space. Okay, but you have this nice effect that the stack can grow, the heap can grow, and they don't have to be relocated, and you solve a little bit of the problem of internal fragmentation. You don't have to give a generous amount of memory here, not knowing how much this is going to grow or how much this is going to grow. You can give a conservative amount of memory to each stack and heap. You can give a conservative amount of memory to each stack and heap and just let them ask for memory if they need to grow. Okay. If you've got a fair amount of physical memory, then you should be able to grow them. If they don't ever need to grow, that's great. You've not wasted internal fragmentation on memory that's never going to get used. Okay. So one thing we see right away is that the multiple base and bounds help solve this internal fragmentation problem. Okay. Now, if you give a process let's give the process, let's suppose that we give the process a fourth base and bounds register. Okay, so let me go ahead and add a fourth base and bounds register and see something we can do with a fourth one. Okay, so here's a fourth base and bounds register. Okay, so that'll be base register 3 and bounds register 3. Okay. Suppose two processes want to share some data. Now, for example, you've seen pipes. Okay, a pipe is when the output from one program needs to be connected to the input of another program. Quite often that's actually done in the operating system using a shared piece of memory. The output from one process is dumped into a region of memory, and then the other process reads from that region of memory. Okay, so if you have a pipe, so suppose now, I'll draw it down here. I'll suppose that at the command line, I lost my mouse. Suppose I had a command line. So at the command line, somebody typed process 0 and pipe it into process 1. Okay, let's see, can I see process 1 is the green one for us. So process 0 piped into process 1. Okay, suppose we had a command where we wanted to do something like this. Okay, process 0 piped into process 1. So that means that the output from process 0 has to go somewhere and the input to process 1 has to read from it. That can be done with a shared segment. So what we'll do is we'll create a shared segment down here. I'll make it purple. Whoops, well, that's not making it anything. I'll fit it right in here. Here's a purple segment. Okay, and I'll make this a shared segment. Oh, I should have drawn the pipe symbol in purple if I was thinking ahead. The pipe is going to be the shared segment. The pipe symbol is going to be represented by this shared segment. Then what I'll do is the base and bounds register for these two processes, they'll share the same values in their base and bounds register. So what that means is this register here will point to that, and this register here will point to that. But that'll be in both of their process, when you switch from process 0 to process 1, they'll both have the same value in BA3 and BD3. Their base and bound register will share a value. That means that they both see the same physical memory space. Okay, they both see it. They both see it starting at address 0. This is another address 0 over here. This is another address 0. Okay, so when process 0 is running, this bounds register. Oh, and if I want to, I could put the shared segment in his program. So he's now got suppose he's got the shared segment right there in his program. Okay. So he's now got a code segment, a stack segment, a heap segment, and this shared segment that's implementing the pipe. Okay. And the other process has got also a code segment, a stack segment, and a heap segment, and it's got the same. It's got a segment that represents the shared segment, and we'll use, so this will be code, heap, stack, and then a shared segment. Now this is really neat because that means that even though these processes are protected from each other, they can still share information in the sense that when process 0 is running, anything it writes to here will be available to process 1 when it's running. Okay, so process 0 can leave information in here that process 1 can read later on when it gets its turn to run. That's tremendously powerful. That's what we call inter-process communication. Okay, and if you Google it, inter-process communication is another one of these huge subjects that makes up computer science. In fact, if you just Google IPC, let's see, inter-process communication. Yeah, IPC, that acronym is important enough that if you Google IPC, you'll get inter-process communication near the top of the hits. Okay, so this is one of the key ideas of computers. For example, networking, the internet was developed as an application of inter-process communication because a browser on my computer talking to a web server on another computer is communication between processes. So all of networking falls under inter-process communication. Now that's inter-process communication between computers. Then there's inter-process communication between processes on the same computer. Right now, we're talking about a simple form of inter-process communication, two processes communicating on the same computer. Okay, and Windows and Linux both have a bunch of techniques for doing this. Shared memory is one of them. Okay, and then there are others, sockets, well, pipes, sockets. They actually, if you go to this page here, they list a whole bunch of domain sockets, message queues, anonymous pipes, name pipes, share. See, here's the one we're talking about, shared memory. Okay. See, it's even got its own Wikipedia page. This idea that two processes through the memory management unit, see, somehow using the memory management unit, you can somehow make it so that two processes see the same physical memory. Okay. Right. So this opens up a huge amount of practical programming things. The fact that you can have two processes share memory opens up huge amount of, that's how, for example, remember how Chrome works? If you go over to the task manager, remember Chrome shows up as just a huge list of processes. And they're all sharing memory. That what they are is, essentially one of the blue process would be one of the chromes, the green process would be another chrome. They can't talk to each other unless they do some kind of inter-process communication like sharing memory. Okay, because the whole point of processes, as we said in our list earlier, is memory protection. So you're isolating the processes, but then once you've isolated them, you want to say, oh, but now we want a way for them to talk to each other. Once you put up a barrier, you want to find a way to get around the barrier, but a controlled way. The idea is a process isn't going to be able to share memory with another process unless it gives the operating system permission to do that. this shared process can't happen by accident. Each process has to be cooperating in this, having this shared memory. So it's, you build up a barrier between the processes, the memory protection barrier, and then you look for a way to punch a hole in it, but the hole is punched by permission. Each process gives permission to share a chunk of memory with another process. So no one of these processes can just arbitrarily reach into some other process. The blue process can reach into its shared segment, and the green process can reach into that shared segment. But each of them knows it's a shared segment. They don't have to trust anything they read in there. You know, whatever data they find, and that's the way modern computing works. You're supposed to sanitize and double check any data you get from another process. All processes are supposed to check the data they get from any other process. Never trust another process. So this is very controlled. So it's you create the memory protection barrier, and then you create the inter-process communication. You create the inter-process communication to allow you have the way to punch holes in that barrier of processes. Okay, so that's one of the big things that memory management, the multiple base and bounds gives us, is this ability to share memory, which can then become part of inter-process communication. In this case, it could be the pipe. Yeah. Process 0 writes things to there, process 0 reads things from there. That they could with a little bit of it's not tricky, it's not easy to do this, but with the right kind of programming, this can be the pipe between them. Okay, so with mobile base and bounds, we've now seen internal fragmentation solved, shared memory solved. Okay, now here's another thing. Can a process have more memory than, now let's look at a different way of using this fourth. Uh, um, Let me think how to explain this. There's a trick now for letting a process think it has more memory than it has. It has more virtual memory than it has physical memory. Okay. I think I should clean up. I should start with a new picture. So let me save this and start over again. And what we'll do is we'll draw a picture specifically for this case here, because it's an interesting case, and it's the case that leads up to the whole notion of paging in virtual memory. So let's think about how we would use this base and bounds register to give a program the idea that has more memory than physical memory. Okay, so what I'm going to do is I want another copy of that picture. I got a copy over here. Okay, so this will be we want to create more virtual memory than physical memory. We want a process to have more virtual memory than physical memory. Okay. So let me give this process several base and bounds registers. Okay. I'll just give it 3 or 4 pairs of base and bounds registers. Okay, there's roughly 4 pairs. Okay, so base, oops. Okay, base 0, bound 0, base 1, bound 1. Now, the trick here is to go and to actually to not think about a program as like this, where it's got one big virtual memory space. Okay. We want to think, not to think of a program like this, where it's one big virtual memory space. We want to think of a program as being made up of what's called overlays. Okay, so here's what I'm going to do. I'm going to think of, instead of thinking of this as a virtual memory space, what I'm going to do is I'm going to call this an overlay. Okay, so call that overlay 0. And then I'll have another, essentially what's a virtual memory space, but I'm going to call them overlays for now. So here I'll have another virtual memory space and a third one, say. Okay, and I'll refer to this as overlay 0, overlay 1, and overlay 2. Boy, I keep losing the mouse. Okay, and each of these has its own address 0. These are essentially virtual memory spaces. Okay, so these are virtual memory spaces with their own address 0. Okay, and we're going to imagine that these are think of these as, well, think of each one of these as something like, where's this. Each one is its own chunk of code with its own program, heap, and stack, but it's all one program. Okay, it's all one program, but the program is divided up into 3 overlays. This was done a lot in the 60s. This was a style of programming that was actually not unusual back then. Now, imagine that each one of these overlays is almost as big as physical memory. Imagine each one of these overlays, when you put it in physical memory, that the overlay would look like this. So suppose this is overlay 1, takes up almost all of physical memory. Okay, so that's overlay 0. Okay, so now let's suppose that the first base and bounds register represents that. Okay. Um, Trying to think, maybe I'm not explaining this the right way. Oh, I'm trying to remember the best way to explain this. I'm drawing a blank now. I'm drawing a blank on what's the best way to explain this idea. Um, the the key is that these three overlays together are way more than physical memory. Each one is, say, in extreme case, you imagine each one of these is a piece of my program, and each one of them almost fills physical memory. So overlay 0 is almost as big as physical memory. Overlay 1 is just as big, and overlay 2 is just as big. But the three of them together make up my whole program. And the way it was used in the old days was like overlay 0 might be the part of a program. It might be, you imagine a program being done in stages where like you're doing the payroll, and the first stage would be to uh, read in all the data about the different employees and process them. And then another stage might be that you would actually write all the checks. And then another stage might be that you do accounting to keep track of where all the money is. Something, it's like there would be three phases to a program. So a program would have phase 1, a phase 2, and a phase 3. And this one be executed. Then when it was done, this one would be executed. Then when that's done, this one would be executed. But each phase takes up almost all of memory. Okay. So programs were written this way in the 60s. It was real common that the program, it'd be a single program, but it would take up a large amount of memory, and the program would be in pieces, and only one piece of the program would be in memory at a time. Okay. It might even be this other picture where this process here might actually say this is its code segment. Okay, like another way to think about it was this process had a code segment, a heap, and a stack, but the code would come in phases. So there would actually be three sections of code over here, but only one of them was used at a time. So there would be one stack and one heap, but three sections of code. So you would have one section of code loaded in here, and then after that section finished, you'd load another section of code into there. Then after that finished, you'd load another section of code into there. Okay, but the three sections of code would share the same heap and stack. That's another way to think about overlays. Okay, so there would be three code overlays here. Okay, and in this case, in this one, we could think of these as three code overlays. Okay, and then there would still be the program would still have a stack segment and a heap segment. Okay, so the program would still have, if we want, we could think of it as having three code overlays and a stack segment and a heap segment. Okay, and then you probably wouldn't have the code overlay being all of memory. There'd have to be room for, well, the stack could be, yeah, so the stack could be, stack could be up here and the heap could be down here, for example. Okay, so now all together, they add up to more than there is physical memory. Three overlays and a stack and a heap. Okay, so together these things add up to be more than there is physical memory. Okay, now when people programmed like this, they would have, in this case, that would be base and bounds would point to the overlay. Then this one would point to the stack. And this one, okay, this would be the stack. And this one would be the heap. Okay, so this one's the heap, the base and bounds of the heap. Okay, and what would happen was when a program got to the end of this segment, when overlay 0 was finished running, it would tell the operating system to copy overlay 1 on top of itself. Okay, And then and overlay 1 didn't have to have the same size as overlay 0. So when overlay 1 was copied, this base and bounds register would maybe change. Maybe there'd be a different, maybe the size of the overlay 1 wouldn't be the exact same size as overlay 0. But the idea was that the program is in pieces. Codes overlay 0, code overlay 1, code overlay 2, a stack segment, and a heap segment. So in this case, it's 5 segments, but only 3 of them are in memory at one time. The stack and the heap are in memory because they hold the data for the program, but then the code will be changing. So there'll be one segment for the code, and these would be 3 different files on the hard drive. Overlay 0, overlay 1, and overlay 2 would be essentially 3 files. The program would be in what are called overlays. It'd be like 3 exe files together made up the same program. They usually probably weren't called exe files, but you'd have 3 binary files that made up the program. And when overlay 0 got towards the end, it would call the operating system saying, replace me with overlay 1. And then the operating system would go out to the hard drive where overlay 1 was stored. It would copy it into this segment and then maybe adjust the base and bounds register because the segment might be a different size, and then continue running the program in overlay 0, in overlay 1. But it would still have the same data here and data here. Okay. The key is that when the program got overlaid, a part of it, in this case, the stack and the heap, don't get overlaid. So a part of the program is being replaced while another part of the program stays in memory. And then the program could switch from overlay 1 to overlay 2. And again, there could be a switch off from, the operating system could be just take this overlay 2, write it in memory here on top of overlay 1, then start executing it. But then overlay 2 would be able to pick up with the data left over in the stack and the heap. So the program, it'd be one program that was continuously sharing the same data, but there would be multiple code segments that could add up all together to be more than there is physical memory of the computer. Okay, so the program itself could be much bigger than the physical memory of the computer. Okay, these were, let's see. There's a Wikipedia page about this overlay programming. People really did something like this, overlay A, overlay B. They're using, and it was specifically a way of running programs that were bigger than physical memory. But because of the limitation of physical memory, so the idea was that you wanted to be able to somehow get past how much physical memory there was. But you needed these multiple base and bounds register. See, it would be a lot harder to do this with only one pair of base and bounds register. With only one pair of base and bounds register, you'd have to have some kind of, let's see, where is the, if you had only one base and bound register, so that was this whole virtual memory space, you'd have to somehow overlay just this little chunk of this memory space. You'd have to like overlay this. Now that would keep this in here, but that was programmatically much harder to do. It would, like, if this program segment was bigger, if one overlay was bigger than the other overlay, then you'd have to move the heap, for example, to make room for the second overlay, unless you made this segment big as the size of the largest overlay. Okay, so you could make this segment the size of the largest overlay. Okay, but it was kind of hard to do this if you had only one base and bound register. If you have multiple base and bound register, you could allocate one base and bound register to the code overlay, okay, and then the other base and bound register could be to the data overlay or to a piece of code that was shared by the overlay. There might be a chunk of code maybe you have overlay 0 stays in memory all the time, and overlay 1 and overlay 2 are the ones that come in and out. So maybe this is cut in half, and overlay 0 sits here, and overlay 1 is down here, and overlay 1 gets replaced by overlay 2, but overlay 0 stays in memory. People did all kinds of funny things this way. But by cutting the program up into pieces, into what they call segments or overlays, by cutting the program up into segments or overlays, you could have them be copied in and out of memory. That's why the Pentium has segmentation in it. The Pentium has this overlay built into it. People who wrote assembly language programs in the 80s on Pentiums used this all the time. They would write their assembly language program in chunks. Some people call them overlays and some people call them segments, and they could load one segment on top of another segment. And then they would have other segments that stayed in memory that held the data, like the stack and the heap. Okay. So with some playing around, you can actually get a program to be huge. You can have programs that are bigger than physical memory. This was used a lot like for Photoshop in the early days. This is how Photoshop worked in the early days when you would try to edit movies or you try to edit pictures. Now we have other ways of doing that, but in the 70s and 80s, when people wanted to do things like manipulate a big picture or try to use a computer to edit a movie, this was an example where they would use this kind of thing. Okay, all right. So multiple base and bounds registers give us more than one single base and bound. You know, so we go from having just these properties to be able to add these other properties. When we added multiple base and bounds register, we could solve internal fragmentations, share memory, and actually have processes with more virtual memory than physical memory. Paging does all of this and more. So we'll see that for example, the one big thing that's really bad about this is the solving the external fragmentation by relocation is tremendously slow. So it's a really lousy solution of external fragmentation. Okay, if you go back to that other picture, when you want to squeeze somebody into this thing, there's a little bit of free memory there, a little bit of free memory there, a little bit of free memory there, a little bit there, a little bit there, a little bit there. You can slide everybody up and get a chunk of free memory at the bottom. But boy, is that slow. Okay, so the relocation to solve external fragmentation is probably the biggest problem with this. Okay, and its sharing of physical memory is not as versatile as we could want it to be. So when we go to paging, we'll be able to solve this way better. Okay, which also solves this because growing and shrinking a program involves relocating other programs. Okay, so this is probably the biggest problem. To relocate to solve external fragmentation, to grow and shrink programs, you've got to copy programs from one place in memory to the other. Paging is going to solve that problem in a really elegant way. And then it'll actually end up making everything else work better. It'll solve this problem well, and it'll make everything else work a little bit better. Okay, so we'll quit there. So that's paging, and I'm sorry, that's segmentation as multiple base and bounds register, and then we'll see how paging's, it's not really directly based on this, but after having thought this way for a long time, I think now you're kind of like ready to accept how paging is going to work. Okay, anybody got any question? Any question before we quit? Okay, so we'll start the page virtual memory on Wednesday, and then we can talk a little bit about the homework assignment and how it relates to. The homework assignment doesn't directly use paging, but it's a little bit based on paging. So it's virtual memory / paging combined. Okay, so stop sharing and meet again on Wednesday. Okay, bye.